Welcome to Switching the Engine, getting some insights into what makes Kubernetes run, or at least from a DNS perspective. So a bit about me. So I'm Michael, maintainer at CoreDNS, contributed to Kubernetes since before version 1, and running an open source research lab called Oco Labs, and supporting companies via record solutions, focusing on Kubernetes, Google Cloud, CoreDNS, and a few of our projects. So some of the things we do, we run a global Git-based DNS provider. So basically, you give us your repository with your DNS files, and we will propagate it to like 40 different POPs, our own IP prefixes, and things like that. And then we, on the open source side, we have an open source project called TextDirect, which is a DNS text record-based redirect engine for your vanity URLs, like container vanity URLs, Git vanity URLs, or just your URL shortener. Basically, it's all about controlling data and controlling the entry point, even so you use a proprietary service or even a free service like GitHub. So let's jump into what the talk is about. So we will first jump into the background. So what are the different ways of doing DNS? What did change in the last few years? And then we jump into DNS issues. So not just DNS issues in general, but what might be done in your cluster, or what might be running wrong in your cluster. And then the two different solutions, or at least two different ways of a solution. One is here's an easy way, deploy it, be happy, and hopefully it works, which is a cluster add-on. And the other one is you're having a really huge problem with your application. It's really specific. You need to have more flexibility, and maybe even the flexibility of CoreDNS. And then basically how to do that and some ideas. And then the general outlook, and hopefully we have time for a few questions. So let's jump into the background. So the primary use for DNS within Kubernetes is service discovery, and basically gluing everything together. So in that note, it's essential to running a Kubernetes cluster, even so it's not called a core component. It's basically deployed on top. And as you all know, DNS is used internally and even externally to access your database, to request files, and send email and things like that. So enter Kube-DNS. So Kube-DNS was the legacy way to do things. Or basically, Kube-DNS was the way the cluster DNS was provided before version 1.11. So what did it do, and what was it? So it was a bundle between DNS mask and SkyDNS. So DNS mask is probably you're already familiar with. DNS mask is usually used as a cache, but also might be known to you as a Linux-based or Linux distribution provided DNS forwarder. In the bundle, it was just used as a cache. And everything basically went through DNS mask and then into SkyDNS that did the actual DNS handling and upstreaming of queries and things like that. So SkyDNS might be something that you're not familiar with. It's a component that is pretty hidden away, and therefore you're not really exposed to it. So it was a DNS server written in Go. It was written by Mick Gibbon and a few others. It's sort of partially maintained. So one of the reasons the switch was done to CoreDNS was more flexibility, more maintainable code, and not relying on something that is only partially maintained. So now jump into CoreDNS. That's basically not just the way to do cluster-based DNS, but it's most likely already running inside your own cluster. So since version 1.11, it's basically GA. Since 1.13, it's the default in almost all installs. So if you have installed, say, 1.14 with Kube-ADM, CoreDNS is already running in your cluster. A small note on that, the cluster DNS service that you might create into configs or add in there is still called Kube-DNS for legacy reasons. But the actual queries are done by CoreDNS on the backend. So what is CoreDNS, and just jump over the general history here. So it's again authored by Meek Gieben. And the legend is he created CoreDNS because he wanted to have Prometheus metrics inside his bind DNS server. And bind seemed to be kind of hard to add new features. And I mean, what we all do is just create a new DNS server from scratch because we want to have metrics, right? So he did that. He sort of started forking Caddy, which is a Go-based web server, with a really flexible plugin and middleware system. So he forked it and then worked with the maintainer, Matt Holt, to basically make it more integrated. So DNS is just one networking plugin inside of Caddy. So it's based on a really performant and really stable core, basically. And Caddy recently switched to version 1, and that's already used in CoreDNS. So it's really flexible. So let's see what we can do later. So the flexibility is not just because of plugins, but also on the modern, or at least modern language. So a lot of things sort of come out of the box by using Caddy or a nice base system. So different protocols are supported. The legacy protocol, if you want to call it that, is UDP. So that was described in the RFCs 1034 and 1035, and was basically version 1 of DNS. It's still widely used, and it's basically the first iteration. It doesn't have connection tracking. It is susceptible to packet drops of UDP, and then you go into timeouts, but we will see that later. The upgrade you can say is TCP. So it's a more reliable connection protocol. It's connection-based, so packets can be resent, so you don't run into your application timeouts because TCP will just resend the packet. But it does have more overhead. Then we have DNS over TLS, which is basically just encrypting the DNS traffic on port 853. And then the idea on a privacy perspective with DNS over HTTPS is you not just encrypt the traffic, so no one can look at it, but you mix it with the usual HTTPS traffic, basically on port 443. So you can't just block a specific port to prevent DNS. You would have to block the port 443 and therefore invalidating all encrypted traffic, which is much, much harder to do. And DNS over HTTPS, or DOH, is supported by Cloudflare and also Google's public DNS servers. And then a more experimental thing is DNS over gRPC. So the current implementation just wraps the DNS packet inside of gRPC. So there's no real native magic going on yet. But we'll see how that goes in the future. And there's no RFC yet. So jumping into the switch specifically, another reason why the switch from Kube-DNS to CoreDNS was done was performance optimizations. So it was hard to add new things in SkyDNS. And with the plugin system, we could modularize the whole system. And because of how it was set up, by default, when we benchmarked everything, it turned out to be either in a proximity to the old way, Kube-DNS, or even better. So Chris O'Haver, back in 2018, so take the numbers with a grain of salt, but there was just no reason to run them again because CoreDNS is basically now used in most things. So we can see here, with the same query load, the memory allocated by CoreDNS is a lot less than with Kube-DNS. So on a memory perspective, that switch already was worth it. On a query side, we're in proximity, and since 2018, there were a lot of performance optimizations. So most likely, CoreDNS is not just better in memory allocation, but already better in CPU utilization and query processing. If you feel like you still want to do, you didn't do the switch yet, and maybe you want to run the benchmarks again, take a look at the work from Chris O'Haver, and if you ran them again with the current versions, please tell us the results, tell us what you found, if that is something that you want to do. So let's jump into DNS issues, the nitty-gritty of IP tables and networking. You're just joking, it's general. So what is DNS? So basically the prerequisites of the problems or where they come from. So DNS is basically a child of the early 80s. So the assumption of DNS back then was it's mostly static, it doesn't change a lot, and therefore it doesn't need to be real-time in that sense. So there weren't that many high-performance, latency-sensitive applications back then. So the compromise DNS was using was basically the network is pretty tiny in bandwidth. The network can't handle a lot of overhead. So the preferred way is UDP. UDP is less overhead. And additionally, with that, never, or preferably never go up to TCP. In our current environment, we would love to have DNS just do TCP, but not every application does that, and not everybody knows about it. So we have to fix it internally in Kubernetes so that it works out of the box. So reiterating that point, before it was basically congestion and availability was more important than consistency of records and reliability of the records. So the old decisions, basically, we can't really, or they can't keep up with the usage patterns right now. So using DNS as a load balancing mechanism, basically having TTLs of below than 5 seconds, are just not workable in that specific legacy idea space. So especially the RFCs 1034 and 1035, specifically ask implementations to let requests only occur over UDP. And secondly, the preferred way is always UDP. That was basically the reasoning, as we said, to lower the overhead for networks. And the retransmission, also for lowering the overhead, was 5 seconds, or at least 2 to 5 seconds. So currently, that would work perfectly if we had reliable network. But as we all know, no network is reliable. It varies wildly between cloud providers. So we did a benchmark in 2018 where we tried to induce UDP-based failures. And with one cloud provider, we actually had to write a proxy that induced that failure. Another cloud provider provided that failure out of the box. So with that decision come the defaults. So the defaults in your resolve configuration turn out to be quite high still. So they didn't change it. It's really hard to change these defaults because legacy application just rely on that. So the result is you might have already seen in logs or latency graphs the 5 to 15-second timeouts. Where did they come from? So we first have in libc, which is using the resolve conf, we have timeouts of 5 seconds. So that's the default. Sorry. That's the default. And then we have the retry attempts, which is by default two retries. So in a worst case scenario, with the default set, you have a 10-second timeout because your network might be unreliable or just because of a UDP packet drop. But there are different things. It's not just the network being unreliable. It's also that the kernel has a thing called the contract table, and UDP is filling up that contract table. So why does it do that, and what's basically the contract table? So the cluster DNS is a normal Kubernetes service, and it does DNet translation. So basically, if a DNS query comes in at that cluster IP, with IP tables rules or VPS, it will move that to the pod IP to basically make the query end up where it should be. But the problem is this rewrite and basically using the cluster IP fills up a specific table called the contract table, which is used for connection tracking. With TCP, that's not a huge problem because usually TCP connections persist, and if the connection is closed, the TCP connection will remove its entry basically out of the table. So it's hard to fill up. The problem with UDP is it's a connectionless protocol. So it still does write an entry into the contract table, but it will never close. And the timeout, the TTL of that specific entry is really high. So the longer something is running, especially like Node.js applications, they love to not cache DNS requests and will just hammer the DNS upstream. You will run into basically filling up the contract table. So it doesn't also, like one thing where people might think that you can circumvent that is using different proxy modes. But both still use IP table rules and both still use contract on the lower end. So, and also like one of the defaults is that the contract table by default is really small. So you could bump it up to like 500,000 entries, but that still most likely will make you run into issues. So one thing that Kubernetes does is it multiplies the problem. It does that in two ways. One is mostly application specific, because usually an A and quad A record is requested. So you already have, instead of one DNS record, DNS query, you have two. And now you run into the Kubernetes search path. So the search path is basically the local resolver trying to guess local and then going up to the absolute DNS name. So what the default search path in Kubernetes is really horrible. So it tries a lot of combinations. So that most likely 10x's your load on a normal application. So makes it easier to run into network issues. It does fill up the table even faster. And we can't really change it because a lot of the applications out there in Kubernetes rely on the search path. So we don't have the ability in Kubernetes itself to optimize the search path later on. So what's the solution? So the easy solution is Node local DNS cache, which is a cluster add-on. You basically just deploy it, and it will spin up a Daemonset, basically a CoreDNS instance on each of your node. It will basically look like this. So you still have the Kube-DNS service, and you still have the IP translation, but it will reduce a lot of things. So if the client pod basically does a query, it could hit the cache, which is local on the node. So that can still happen over TCP or UDP, but usually your local host doesn't have UDP packet drops. So you already circumvent that problem. If you miss the cache, which hopefully isn't that often, we still have to upstream, but then we can optimize further because now we control not just the cluster DNS, but the client side of that cluster DNS. So to jump into the specific fixes, basically, we skip the contract table. So to make that rewrite possible, so each pod automatically now talks to the node local DNS cache with a specific rewrite rule in IP tables, which basically uses a local private IP and adds a rule that the contract table isn't used for that specific IP. So locally in the node, we will basically circumvent using the contract table. Usually that's a problem, but because we are local only, that's not an issue at all. So we circumvent the contract table on that regard, and therefore overflowing it. We still have the same issue going from the client or the node, local one, to the DNS cluster. But we already reduced the upstream query load at the same time. And due to the ability to upgrade connections, because we control the client and the server, we can upgrade to a TCP connection. So UDP comes in, we upgrade the connection to TCP. Because we only connect to one upstream, we can persist the connection, so reducing the overhead overall. So we reuse the same TCP connection for all incoming queries, and basically have a standing connection to the DNS upstream, which furthermore circumvents UDP being dropped into the contract table, and at the same time removes any reliability issues because of the network with UDP packet drops. So another thing that is being fixed is external lookups. So usually external lookups will create a lot of load on the cluster internal DNS service. And what node local does, everything that is not cluster internal, so it doesn't need to go to the central CoreDNS, will exit the node right from the node and then go to an upstream server. That usually is your cloud provider. So that's really helpful. So you're basically fanning out the whole load of all your external queries to each node. So if you add a new node, you basically get new limits from your cloud provider. You get new capacity to push to the upstream, and it usually is much, much smoother. So, and the bonus, you basically get per node DNS metrics. So if you feel that someone is spamming your DNS or server with queries, you might want to know which node it is. And we jump into a solution later where we can even granular push it down or pin it down to a specific pod. So let's jump into a small benchmark. So that's basically the latency without node local. So the setup is we have two Kube-DNS or DNS service pods. We have 240 pods generating DNS load, and we have 3 nodes in total. So the overall query load in that benchmark is around 200 queries per second per DNS cluster service, basically. So we can see from the left, it basically works perfectly. It's like a few outliers that might be UDP packet drops, or it might be just general problems. And then the longer it's running, the more we fill up the table, and then we jump right into the 5-second timeouts, which you can see here. So we basically see a huge tail latency because of the timeouts, and it will only get worse because the table will just, or because of the contract table, it will just, from the kernel side, drop UDP packets because it's full. And now with node local. So with node local and all the optimization that brings, we just don't run into any 5-second timeouts anymore. So we basically optimize the latency out of the box by just deploying one cluster add-on. So what's the difference compared? So where do you think we deployed node local? Correct. It's on the right side, where we basically don't have any tail latency anymore. So what's the future of node local? So it's coming in version 1.15. It's going better. So it's not just something that you might try out in your test setup. Please actually see if you could use it in production. If it helps you, please provide feedback. Really helpful to go GA and to know your use cases to see what we can do. Especially, there are 2 proposals. One is called AutoPath. So we talked about the search path problem in Kubernetes. And one idea is using eDNS 0, which is basically the possibility to add metadata to a DNS query. So we're using that to do the search path translation or resolving of that search path on the server side. So the client queries for, say, your application .service, for example. And usually it will go through the whole search path. But the query basically gets metadata, which pod in which namespace is actually creating the query. And then the global DNS cluster service can then use that metadata to resolve the whole thing. So it will give back the final answer. So you will have one query instead of the 10 different ones for the whole search path. Bonus point is because it's transparently resolved, it basically enables us to cache that. So we have even more performance optimizations possible later on. And another thing which is really neat, or which does really need your feedback, is HA for the node local Daemonset. So is that something that we really want to do? Because it's a per node basis. So we already have a per node thing that basically we have the Kube proxy, which is a single point of failure. We have the node that is usually hardware limitations as a single point of failure. And in general, everything on a node level is basically subject to a single point of failure already. So why would we go HA on one specific thing if everything else could already fail? But that's being proposed. So please go ahead, tell us your use cases for that specific idea, and maybe we can work with that if that's actually something that we should do, or if that's just complexity that's not necessary. So let's jump into the second, more customized solution. So the recommendation here is still go with the default cluster add-on. It's just easier to to work with. It receives update without you having to know a lot of things, and we can optimize on our own schedule within Kubernetes. So the first thing that you can do to customize is basically customize the cluster on itself. So you will still have the general idea of a daemon set running on each node, and therefore a local DNS cache. But you can also tweak the YAML and in general like the cluster add-on. So in this specific case, we can see here that we added the prefetch. So we already have a cache, but the problem is if you request a lot of different DNS names or queries, it might not hit on the first try because it's a cold cache. So we can prefetch hot records to basically circumvent that and further lowering the tail latency. So in this specific case, we're basically saying, OK, use prefetch with a 1, which is basically 1 query per hour. So if the CoreDNS local node local basically sees 1 query in an hour for that name, it will prefetch the record from the upstream once the TTL is under 50% of the general TTL. So we get a bit more responsive. We can lower our TTL because we prefetch, so we don't have a lot of performance issues with that, and basically drop tail latency even more. What you can also do is tweak the settings on the cache size. How much negative and positive caching is done. Negative is usually done on errors. If you can't find anything or something, that's usually cached. That's also something that wasn't there before. DNSMask doesn't cache by default negative queries. So if you have a lot of search paths which end up not being a correct record, you don't even cache that. So it actually makes the load even worse in the legacy system. So that's basically the simple customization. But what's the going all in on customizing and flexibility? It's basically using the sidecar model. So deploying your own CoreDNS instance right next to your application. So you have a local cache inside your pod. So that might already be helpful. So you can control the cache size much, much easily. It's not from the operations side or your platform team. The application team can actually tweak the settings. So that might be really nice for them not to spam your system and also have full flexibility on what they actually want to achieve with DNS. As we said, because it's CoreDNS, you can have the full flexibility of CoreDNS. And we'll see that how that might be impacting in a second. And then you can do application-specific optimizations, such as your own choice of upstream servers. It might have a specific external cluster DNS or something. And it could do specific caching. So someone came up with, they have a flaky upstream server. So sometimes there's a negative response, even so it should be positive. And the problem, how they solved it, was not cache negative responses, because then it will just require, at least the second query will succeed, which probably is you should fix your upstream servers, but anyway. And then you can rewrite queries. So CoreDNS has access to rewrite not just the response, but also the request. So you can change per regex the request name, the request, and even the response data, and add new data with eDNS 0. And then, as an added bonus, you get per pod, per application DNS metrics. So if you have a scraper that does a lot of different DNS requests, you might have more insight into how to cache something, how to tell your customers to lower their TTL or make their TTL higher, depending on what the metrics say. So enter our application. It's text direct, DNS text record-based redirects. So you control your entry point, your data, and it's open source based on Caddy. The interesting thing here is each incoming request will result in at least one DNS request. So it's a really DNS request-heavy application, which we use to benchmark. The request flow is basically, if your browser hits Kubernetes does open source software.rocks, because we know that's true, it will first pull down the A or quad A record or the C name, and then connect to the server, either self-hosted or our servers, and then the server will pull in the data of the actual redirect, which is as a text record with underscore redirect .kubernetes.opensource.rocks, which gives us back the data we need to do the actual redirect. And then we actually redirect to kubernetes.io. If you want to have more information on that, textdirect.org has a lot of information. So what's the sidecar configuration in that specific case? It's still simplified, but you can see a lot of things. Firstly, it's your own custom upstream server. So you circumvent the upstream servers in your cluster. It enforces TCP, so we upgrade the connection. And then we do a few things further. The cache can lower the TTL, so the maximum TTL that is allowed. Because we pull in customer-based DNS records, and they might have a huge TTL, we want to prevent caching stale records. So we enforce a low TTL of 2 minutes maximally. So that's the max that is in the cache, and then we repull afterwards. That creates a lot of load. So we use prefetching to basically, if we see it once in 24 hours, we will repull it after 30 seconds, which is really helpful. So we pre-fill the cache even for sites that don't receive a lot of traffic. And then as an example, what you can do with rewrite, you could rewrite an external service to your own cluster cache. So the application still thinks it's talking to S3, but it actually isn't. It's talking to the pass-through cache of that object store in your cluster, and the rest is handled by that specific service inside your cluster. And it can do a lot more. So what's the outlook? General performance improvements in CoreDNS. It's full and continued scale testing in Kubernetes. So if you want to take that up, definitely reach out to us. We have resources, but time is limited. Search path optimization has a cap open. And we would love your feedback to how to do that. And basically, what's really interesting on the roadmap is watch-based record updates for Node Local. So instead of getting a query in and then forwarding it upstream, we could pre-fill the cache by asking a GRPC-based API from the API server to basically pre-fill the records and also renew them on changes or renew them to never be cold. And that would really improve consistency and reduce the downside of having huge and long TTLs. So happy to hear your feedback and ideas. There are 2 links. One is the CoreDNS repo, and one is the Node Local DNS repository. And happy to take a few questions. We have a few minutes left. Please keep the questions general. DNS usually is really setup specific, but we can talk about the personal setups after the talk. Any questions? All right. Any problems that ever came up with DNS? Yes.
Kubernetes services on real time.
Yeah.
We see that sometimes the service creation takes 6 seconds to 10 seconds for DNS to reflect. So what could be the problem happening there?
So the problem is that consistency in general with the API server is already lagging behind. And then you might have already requested the record, and just the updating of the API server is usually the problem. Because how CoreDNS pulls in the records, it will talk to the API server directly and then reflect updates. But that might take a bit. So if you need real-time updates, Kubernetes already doesn't provide that. Because the creation of a service record might not be fast enough for you to actually do real-time discovery.
So that's like problem is, can it be solved somehow? Like that is like we are waiting to return back until the DNS entry is done.
So don't rely on it being perfectly consistent in the first 10 seconds. So that's generally a rule for service IPs in general. If you really want to do something, what helps is usually have health and readiness checks, because then the cluster internal kube proxy basically can do the redirecting better, because it will only enable the service IP or the cluster IP redirect once it actually knows the service is ready. If you don't have that, you usually have like a inconsistency problem in general. Thanks.